This is a review of thermo. I chose the mean endothermic reactions. I studied them before they were cool. Just as a reminder that if the temperature drops as a reaction occurs, then that means it's absorbing heat overall and it's endothermic. If the temperature goes up, that means it's exothermic and it's releasing heat. To calculate delta H, which describes a system as being endothermic or exothermic based on its sign, we first need to look at its units. The units for delta H should be kilojoules per mole of reaction. As you can see, this combustion reaction has a delta H value that is negative, which tells us that this is releasing heat or exothermic. The units for that are that many kilojoules per mole of that reaction occurring. And that energy value goes with every coefficient in that reaction. So when we're asked the question, how much heat is released if 12.3 grams of oxygen is burned in the presence of methane gas, heat really is just asking about the energy in kilojoules. So again, this is really a version of stoichiometry. So because we have this balanced chemical equation, we can use the moles as mole ratios with the energy value that was given, delta H. So our first item is to change 12.3 grams to moles, and then we can use the energy value that's given and relate that to the amount of oxygen involved in this combustion reaction. So here's how it would be set up. 12.3 grams of oxygen divided by the molar mass of oxygen times the delta H value per 2 moles of oxygen. Again, this energy value goes with every coefficient, and so since we're asked about oxygen, then it's per 2 moles. So overall, this is negative 171 kilojoules, or that much heat is released. With Hess's law, when we know we have this kind of situation, we'll be given several reactions, 2 or more, that have individual enthalpy values for those individual reactions, and then there'll be a different reaction, and we're asked what is the enthalpy change for this other reaction. Our goal is to add the individual reactions together so that some substances actually will cancel out. We want to end up with the overall. If we can add the individual reactions together and end up with the overall reaction, that means we can also add together their delta H values. As we're looking at the different reactions, and we'll see an example in the next slide, we might need to manipulate the individual reactions so that they will add together to come up with this new reaction. So notice the first bulleted point mentions that if we need to reverse a reaction, we also would reverse the sign of delta H. Because a reaction is in one direction exothermic, if the reaction is reversed, the energy stays on the side that was reversed, so then it becomes endothermic. Also, if we need to change any coefficients so that some substances cancel out or that coefficients match the overall reaction coefficients, any change we make to coefficients, that change also needs to be made to delta H, and we'll see that on the next slide as well. So this is what a problem would look like where we would know to use Hess's law. So notice we have 3 individual reactions. They each have their own delta H value. They just all happen to be exothermic. And we're asked, what is the delta H value for this overall reaction? So as you're looking at, it's a lot of information, and typically these kinds of questions can be relatively simple. You just have to know what to look for. So take one of the reactions at a time and look what in this first reaction is also in the overall reaction. And if you'll notice, after looking at all the reactants and products, I'll notice only this C2H2 is in both. So because it's a reactant in the reaction I'm given, but I really need it to be a product, that is an example of where I need to reverse this reaction, which means this sign is going to get changed. So I could just say multiply times -1. So now it will be a positive delta H when I reverse that reaction. Going on to the second reaction, I can see the only thing in this reaction that's also in the overall is this carbon. solid carbon. The problem is I have a 1 coefficient and I really do need a 2. So that tells me I need to multiply this whole reaction by 2. And if I do that, I also have to make that same change to its delta H, because each mole of each reaction gives off that much energy. So I've doubled the reaction, I've doubled the energy it's going to give off. And if I look at the last reaction, I do see all that's left is hydrogen. I do have hydrogen as a reactant. In this last reaction, it's a reactant in the overall I'm trying to end up with. The coefficients are right, so I don't need to make any changes here. So again, as a review, I'm going to reverse the first reaction, multiply the second one by 2. So really all I need to do after I do make those changes is add these all together. And we'll see all these changes on the next slide. So I've kind of recapped it. I reversed the first reaction. Notice the sign was changed. It's circled in blue. I multiplied the second reaction by 2, so I've changed all these coefficients in this reaction. Notice I've also multiplied by 2 to delta H. No change to the third one. Adding these circled values all together, I should end up with an overall positive 226.8 kilojoules per mole. Therefore, this is the energy value that goes with this reaction at the top, and that is an endothermic process. Another way to calculate delta H is if we're giving enthalpies of formation. These would be in the form of a table. We would have a reaction. We would be asked what's the enthalpy for the overall reaction. Occasionally, maybe they'll give you the enthalpy of the reaction. They might ask you to solve for one of the individual enthalpies of formation. But the key to this is when you see enthalpies of formation, this is the formula you know to use. This is on your formula sheet. It's set up. It's very easy to use. It's the sum of all the enthalpies of formations of the products minus the sum of all the enthalpies of formation of the reactant. So it's just like that on the formula sheet. The only thing you really need to remember is, and this, if I noted this, each of these enthalpies of formation is per 1 mole of the substance. So if there are other coefficients other than 1s, we would need to multiply any of these terms by their coefficient. So we would take into account that we had more than 1 mole. So doing that and summing it up, we'd have our answer. Moving on to another table of values, if you see a bond energy table where you see these covalent bonds drawn and they're telling you the energy that would be required to break these different types of bonds, this formula is not on the formula sheet, so that's one thing to note. And you just need to think about the reaction. Reactants are broken, bonds are broken in the reactants, so this is the broken, so that's the reactants, minus the sum of the bonds that are formed in the products. Okay? So it's sum of the bonds broken in the reactants minus the sum of the bonds broken in the the bonds formed in the products, because when bonds form in the products, they do release energy. And I talk about this again in the bonding review. You must draw the structures. If you don't draw the structures, you're going to forget a bond. You literally have to count up how many bonds in the reactants are broken, count up the number of bonds, multiply the bond energy number by its corresponding value, sum all the reactants, bonds that are broken, don't forget coefficients, minus, and then sum up all the new bonds that are forming that are going to be releasing energy. Whichever sum is greater will tell us that the overall delta H is endothermic or exothermic. So if it's positive, we would know it's an endothermic reaction overall, and if we get a negative answer for delta H, we would know it was exothermic overall. This graph represents a covalent bond forming. Again, anytime bonds form, any type of bonds form, it's because there's an energy advantage to that. Energy is released when bonds form. So anytime you see this valley graph, always look for the lowest point. That will tell you the bond energy or the energy that's actually released. Notice it has a negative sign. So it's not negative as in below zero, it's negative as a direction. 432 kilojoules per mole of energy is released when this bond forms, and it also tells us how close those atoms are together. Notice it says internuclear distance. That is what we call bond length. So weaker bonds would release, like this is a hydrogen-hydrogen single bond, we would expect it to release less energy than if we were forming like a double oxygen bond, which would have a higher bond energy, meaning it would release more energy. So it would actually have a lower valley. Calorimetry is a lab question, and this is very regularly on the AP exam, so I highly recommend that you make sure you can do this problem because it is a little drawn out. But it's a way to calculate heat that's produced through a reaction or a dissolving process or a transfer of heat, and be able to change that to enthalpy, which is delta H. So starting off, if a calorimeter is mentioned, or 2 polystyrene cups, which is the chemical name of the brand name styrofoam, if anything like that's mentioned, you should think Q equals MC delta T. This is on your formula sheet. M is mass, and we do want to use total mass. So if we have 2 reactants, we're going to add their masses together. If we have a salt dissolved in water, we're going to add those 2 masses together. Specific heat, typically it's of water. This would be given, 4.184. And delta T is final minus initial. So make sure you subtract in that order. It actually does matter. Now, once we have the value for Q, based on all the units that we would have plugged in, those units would be joules. So heat would be measured in joules, but as you remember at the beginning, delta H is kilojoules per mole. So we've got to convert several things to get the correct representation for delta H. Now, number 1, it says because the solution in the coffee cup is the surroundings, the Q of the system is equal in magnitude but opposite in sign from the solution. So literally what's happening is if we have a delta T that if the temperature went up, right, the delta T would have or we could say initial temperature would be lower than the final temperature, so the temperature went up. That should be an exothermic reaction because that meant that solution or the reaction released energy to the solution. However, when we do delta T, final minus initial, we get a positive value. Mass is positive, specific heat is positive. We'll have a positive Q, which would not represent delta H correctly. So our first order of business is whatever sign we have for Q, we're going to change it. So again, if we had Q as positive, then we're going to make it negative. So that's our first thing to do. The next thing is to change Q from joules to kilojoules, because again, our goal at the bottom is to end up with kilojoules per mole, all right, with the correct sign. So if the temperature's gone up, we need to have a negative sign for delta H. Q would end up being positive when we did that math problem. So we've got to change the sign, change joules to kilojoules, and then the last thing is we need to come up with where is this mole, because this is usually mole of the reaction, and really this is going to be moles of the limiting reactant. If we have 2 things reacting, whichever is the limiting reactant, we'll divide by moles of that. If we have a salt dissolving in water, we're going to divide by moles of the salt that's dissolved. Here's a kind of a classic example of a salt, ammonium nitrate, being dissolved in water. Notice the temperature's dropping, so that should tell us, oh, okay, this must be endothermic. The temperature went down. So my delta H at the end needs to be positive, and it tells us our temperature change. Calculate the enthalpy of the solution process. And again, it says the specific heat is the same as water. On the AP exam, that number is in the problem, 4.184 joules per gram degrees Celsius. So, several things we need to do. I see the word coffee cup calorimeter. My first thought is I need to solve for Q. So Q equals M times C times delta T. So I need to get my total mass. The specific heat would be given. I need to calculate delta T. Delta T is not a measured value. You've measured 2 temperatures that you're subtracting. Delta T is a calculated value. So I've got to do 16.9 degrees Celsius minus 22 for my delta T. So here's kind of the whole process. My total mass, my delta T calculation. Notice it is negative because the temperature did drop. Here's my Q calculation. Total mass times specific heat times the temperature change gives me this joule value. Because this is not my final answer, I need to keep unrounded numbers in my calculator until I get to the end of the problem. If they ask me for the heat that was absorbed by the solution, then I would round this to how many significant figures? It looks like we'd have 2 because when we subtract the temperature, we end up with the 2-digit number. So I would have to round it a good bit. But since that's not a question, I'm only asked for delta H, I'm not going to round until I get to the end. So again, here are the steps we need to go through. We've got this Q value, 3 things we need to do. First, we're going to change the sign. It needs to be positive because delta H, if it's endothermic, is a positive sign. We're going to divide. We've got to change joules to kilojoules, and we've got to divide by the moles of the salt dissolved. So here is the mass of the salt divided by its molar mass. Here are our moles. So notice I still have my joules. I'm dividing by moles. That gives me joules per mole, but again, we remembered we needed kilojoules per mole, so I have this very unrounded number. I would never leave it like this on the AP exam. I would round it to 2 significant figures. Positive 26 kilojoules per mole. So yes, this is endothermic overall, which is what we would expect to have since we had a temperature drop. Here's the AP formula sheet. As you can see, we've talked about the calorimeter formula. We've seen this enthalpy of formation where it's products minus reactants. And then notice there are a couple other summation formulas that deal with entropy and free energy. We'll see that in a minute. And then there's a formula that puts all of these variables together and a couple other forms of delta G. And again, several things are defined on the right. It's important you can recognize energy diagrams. The first energy diagram represents an exothermic reaction. Notice the reactants have more energy than the products have at the end. So the difference in where the reactants were and where the products remain, that is the energy that's given off as heat. So the products end up with less energy. The difference is the delta H. It says energy released, that's our delta H. And again, in kinetics, I talk about the activation energy. That's the energy needed to break the bonds in the reactants so that they can form products and release energy. The endothermic graph, again, notice it's just the opposite. Reactants start lower. They absorb energy overall, so our delta H is this, energy absorbed. And then the products, where the products end, is higher because the energy has been absorbed from the surroundings. So we have delta H is negative as exothermic, positive tells us is an endothermic reaction. In any type of state change or phase change, like as we move from a solid to a liquid to a gas, that is requiring energy. Okay, so again, just even physical processes like state or phase changes require energy to be added or maybe energy is released. So as you notice in the first example, energy is added. These are an endothermic process when we break the IMFs between molecules. So like as ice melts to water, some hydrogen bonding is being broken to separate those rings of the ice structures to get them to be closer together, since we know ice is expanded. Ice has a greater volume than water. But when water vaporizes to form steam or water vapor, it requires more energy because all the remaining hydrogen bonds must be broken. So these are examples of breaking IMFs requires energy. It's endothermic. If we go the other way and we start with like water vapor that condenses to water, that then freezes to ice, all of those processes require, the beginning process has more energy. That extra energy's got to be released so it can be in a more organized state and the IMFs can hold it together. So as we see, these last processes are all exothermic. A heating curve is another way to use Q equals MC delta T. Notice at the lowest section, where the temperature is the lowest, that is where we're going to have a solid state. This middle section would be a liquid, and this upper section is going to be a gas. The in-between portions that are flat are where we have the phase change occurring. Okay, so as you can see, this is 0 and this is 100, so this is the melting point of ice and the boiling point of water at 100. It takes energy for those to happen. So it takes energy to raise the temperature. So each of these line segments, there's one or two things going on. If you notice at Q1, 3, and 5, the energy added is just raising the temperature, and that's why we can use Q equals mc delta T. If we know the specific heat of water, we know the mass of water, and we know the temperature change, we could calculate how much heat is required to make water just raise its temperature. If we're asked about how much energy is required to vaporize water or to melt water, we have to know which enthalpy value goes with that. So if we're talking about melting, we would use fusion, and actually you'd use it for freezing as well. And vaporization would be added for vaporization, and that much energy would be released if it was condensing. But here, this is where we talked about IMFs are being broken, and that's where we need to know the mass of the substance. We would change it to moles and then use the correct energy term. Here's an example problem that might be like one you might see. Using the heating curve above, how much heat is required to vaporize 32.1 grams of methane at its boiling point? Okay, so keywords: boiling point. Boiling point and melting point are going to be flat areas. You see the word vaporize. This is the enthalpy of vaporization, so that is helpful. That, you know, that of course they're going to have to give you the information, but hopefully that'll help you pinpoint what part of this curve is important. That S portion that's labeled S. So what math do we need to do to change 32.1 grams to just an energy value? So notice this is 32.1 grams. That is 8.2 kilojoules per mole. Hopefully you realize we need to change grams to moles, multiply times that, and then we have the answer. So this could be a good multiple choice question if the numbers are easy to do without a calculator. When a solution forms, you know, we talk about these ion dipole attractions in the IMF review, but there's really a lot more going into it. Notice this is like NaCl as a solid. So something's causing that NaCl, which has very strong ionic bonds, to break apart. And what is that? It's because energy is being absorbed, and that is an endothermic process. So just the NaCl itself breaking up is endothermic. Sometimes we don't really think about, you know, all the water is very attracted to other water molecules through very strong hydrogen bonding, but when these ions come into contact, the hydrogen bonds, some of those are broken because now a lot of the water molecules, as you see, are surrounding and are attracted to the ion. So there's two processes that are endothermic: breaking up the ionic compound, breaking some of the hydrogen bonding between the water molecules, and then the third process is the one part that's exothermic. When there's an attraction form between the ions and the different partial charges of the water molecules, attractions, just like we said with bonds, attractions release energy. When bonds form, energy is released. So it takes energy to break attractions, and it releases energy when attractions form. So if we add up all these three delta H values, overall, is delta H positive or negative? Well, it depends on the magnitude of those numbers. So when some ionic solids are put in water, like we saw earlier, the calorimeter problem, ammonium nitrate, the temperature dropped. So that tells us that overall, these two delta H values must have been very large positive numbers, and then this exothermic number must have been very small. A lot of ionic solids are exothermic. The temperature goes up when they dissolve in water, okay, like a hand warmer. So what does that tell us? This value, if it's overall exothermic, must have been had a very large magnitude, and being negative. When I added all three of these together, it was overall exothermic. So again, it just depends on the salt and the values of these three individual numbers as to what the overall term will be. Now we'll move on to entropy, which has the symbol delta S. Simply is the change in disorder or chaos. The units here are different from delta H. Notice delta H is kilojoules per mole. Entropy are joules per Kelvin mole. So be aware of that. There are a couple of formulas where not recognizing the difference in units and changing them can trip you up. Delta S is positive. The sign is positive, or it increases when there's an increase in disorder. So like a solid forming a liquid, or a liquid forming a gas. Dissolving an ionic solid in water is increasing disorder, since now you have aqueous ions. And then in reactions, if you're looking for an entropy increase, look for gases, because gases have the most entropy. Whichever side of the reaction has more gas moles or moles of gases, that side of the reaction has more disorder and has more entropy. So if that's the product side, we have an increase in entropy. But if the reactants had more moles of gases, then entropy would actually be decreasing. So again, watch that. We do have another formula that looks very similar to that delta H version, and it is. It's the sum of those entropies of the products minus the entropies of the reactants. Again, you do need to watch your coefficients, because you would be given a table of these delta S values, and you would have to notice that if there's a coefficient, you would have to multiply that coefficient times a substance's entropy value given in a table. Gibbs free energy, or just free energy, is delta G. And this really tells us if a reaction is favorable or not. And when I mean favorable, I mean, is it going to go forward on its own? Thermodynamically favorable means that, and I have that down here on that third bulleted point, that delta G is negative. That means a reaction will occur on its own, meaning it's going forward. If delta G is positive, this is telling us that the reaction is not favorable under the conditions. And so really, the reaction is favored in the reverse. So it is not, the forward reaction is not favored, is the bottom line, for delta G is positive. The forward reaction is not favored and will not occur. Delta G also has the units of kilojoules per mole, just like delta H, so those two do have that commonality. There are two driving forces in nature, and if we have a reaction that contains both of these driving forces, delta G will be negative. Okay, so again, one driving force is an increase in disorder, so that means delta S is positive, and the other driving force is an exothermic reaction, because nature does favor the lowest energy states, and since exothermic reactions release energy, those can tend to be favored. So if we have this combination, as mentioned here, if a reaction is both of these, an increase in entropy and an exothermic reaction, this is the case where delta G will always be negative. It doesn't matter what the temperature is or what the situation, but this is a thermodynamically favorable reaction. However, reactions can be thermodynamically favorable if they only have one of these driving forces. So, and that's what we'll look at on another side. So if they have both, it's always favorable. If they have one or the other, it can be favorable, but the temperature will determine it. And then on the next slide, this is just kind of a summary. There's a couple ways to look at this. I'll start with the signs. As you look at this graph, notice that H is on the X and entropy is on the Y. If we just look at the signs in each quadrant of this graph, you can see that this is the situation here where, and again, this is telling us all the signs to come up with delta G. So if we have this situation, that had the two driving forces mentioned on the other side, where this is exothermic, delta H is negative, and an increase in entropy where delta S is positive. So if we have that situation, delta G is favorable and negative no matter what. if we don't have either driving force, which would be this quadrant here, meaning it's an endothermic reaction that's decreasing in entropy, the never refers to delta G will be positive, it will never be negative. So it's kind of a double negative. But so again, if there's no driving force of those two, it will not happen. And that's what that's telling you. If we have one of the driving forces, that's what I was referring to, where it's the temperature. So this isn't going to happen. The temperature will tell us if this occurs or not. Okay, so let's just take these one by one. If we talk about this low, and low means low T, low temperature. Okay, and what that means, at a low temperature, if I have this situation, delta G will be negative. So again, in this case, the only driving force that's there is delta H is negative. So this is an exothermic reaction, but it's decreasing in disorders, actually becoming more organized. But if the temperature is low enough, then it will be favorable. So it only has one of the driving forces. And again, think about it. Both of these signs are negative. It's only going to happen at a low temperature. So to me, that logically can be easy to remember. Two negatives with low temperature, delta G is negative. Again, the top part of this graph, notice the only driving force here is the delta S is positive. This is an endothermic reaction, which we said was not a driving force, but the increase in disorder is driving this to be favorable only if the temperature is a high temperature. So this is at a high temperature, and that's telling us delta G is negative. Now, this is just another summary of what we've just gone over. So however you want to remember this, you know, I just remember the two driving forces and know that if the signs are the same, it takes a high temperature for delta G to be negative. If the signs are both negative, it takes a low temperature for delta G to be negative, and then I know the always and never. There's a way to look at it in this table, but really you almost don't even have to memorize these. If you just plug in signs to this, this is a very important formula that relates all these to each other. You can figure out the signs just from using this formula. So this is on the formula sheet. If you're having trouble kind of understanding this, you can actually use this and say, and let me just kind of work through this. I'll do the always one. If delta H is negative, again, we're subtracting, but we're multiplying temperature times delta S. And when we use temperature, most formulas we have to have Kelvin. So this temperature can only be a positive value since all Kelvin temperatures are positive. So if I take these two always terms, signs, and I plug in the delta H is negative, and I plug in a positive sign for delta S, I have a negative minus a positive, or really I'm adding two negatives together. So the only answer I could get here is going to be a negative delta G term. So if I go through and do that with each situation, you'll see that that is, you know, again, that's on the formula sheet. That might help you to remember how all these relate to each other as well. I do like this graph. Here are all the delta G formulas. Again, this is the third one that looks similar. There's that enthalpy and entropy one as well. We've talked about this. One thing I haven't mentioned from my previous slide is this is where I mentioned earlier you need to watch the units. Delta G and delta H are both kilojoules per mole, but as we said, entropy is joules per Kelvin mole. You must change. You typically entropy to kilojoules, and then you can do your math correctly. Otherwise, you're not going to be anywhere close to the correct answer. You'll be 1,000 off. Here's the electrochem connection for thermodynamic favorability, and then here's our connection to the equilibrium with the equilibrium constant. And this is a nice summary table that reminds us that if we have a positive cell potential, K must be greater than 1 because the reaction is going forward, and that's what we're looking for, a favorable reaction. If we have the opposite of that, the reaction's not going to happen. You know, again, think of positive as an X. That means the reaction doesn't happen. And if we do have, like we call our cell phone battery as being dead, it really just means it's at equilibrium. Okay, and there's, you know, it's not producing any voltage, so we have 0 for delta G and the cell potential.